My name is Peng from UCSB. I will introduce our work, iPIM, Programmable In-Memory Image Processing Accelerator using near-bank architecture. Nowadays, there are an increasing number of devices that generate large quantity of image data, such as smartphone cameras, traffic cameras, medical imaging equipment, and satellite imaging. The majority of these image data will be stored in data centers or workstations for further processing. Based on the huge volume of image data, the improvement of algorithms have created many important application domains, such as machine learning, traffic analysis, medical image processing, and geographic information system. Since image processing workloads are time-consuming and memory-intensive, data centers can benefit from image processing accelerators that provide domain programmability, high performance, and high energy efficiency. From the application perspective, image processing workloads have some characteristics that require customized accelerator design. From a high level, image processing algorithms consist of pipeline stages that are both wide and heterogeneous. First, for most of the individual pipeline stages, they are wide. Here, we will use image blur as an example to show this. Image blur is the process of using an image blur filter to scan over the input image as shown in this figure. At each location in the input image, a filter computation will be performed between the image blur filter with the corresponding input image region, and an output pixel will be produced. First of all, this process exhibits massive memory level parallelism among pixels, as the image blur filter can be independently applied to different input regions. Second, this pipeline stage will generate large size of intermediate results on the same scale as the input image. Third, these computations usually have low arithmetic density, which means on average, few computations are performed for every byte read from the main memory. Then, for the overall image processing pipeline stages, they are heterogeneous. Here, we use local Laplacian filter as an example to show this. This process involves different kinds of pipeline stages with diverse memory access and computation patterns. Furthermore, the complex data dependencies, as shown by the edges in this graph, makes it very challenging to perform pipeline fusion, which is a technique to improve data reuse among different pipelines. We conclude that image processing workloads have high memory bandwidth demand. From software view, they show low temporal data reuse because of low arithmetic density and difficulty of pipeline fusion. From hardware view, the on-chip cache cannot hold all intermediate data, so large off-chip memory traffic will be generated. To demonstrate this memory bandwidth bottleneck, we profile a set of representative benchmarks using state-of-the-art GPU accelerator. In this figure, the horizontal axis shows the benchmark names. The left vertical axis shows the measured bandwidth, and the right vertical axis shows the utilization of DRAM bandwidth and ALUs. The results show high memory bandwidth utilization in comparison with very low ALU utilization, which means significant memory bandwidth bound behavior. Furthermore, to show the effect of pipeline fusion, we also compare single-stage kernels and multi-stage kernels with pipeline fusion optimizations. We found that after pipeline fusion, there is little improvement in ALU utilizations, and the DRAM utilization is still high for multi-stage kernels. We conclude that pipeline optimization does not change memory-bound behavior of image processing workloads on GPU. Next, we show that GPU, which is the state-of-the-art image processing accelerator, is unable to meet the challenge of bandwidth scaling. GPU can provide the highest peak memory bandwidth among contemporary hardware accelerators by using high bandwidth memory, or HBM, as shown in this figure. It allows multiple DRAM dies to be vertically interconnected by through-silicon vias, or TSVs. However, as a compute-centric accelerator, GPU suffers from bandwidth wall as the number of off-chip IOs, or TSV numbers, cannot scale with computation throughput. We know that the raw memory bandwidth equals to the number of IOs multiplied by the data rate per IO. First, increasing the number of IOs is difficult under tight area budget, since there are limited off-chip pins. Also, TSVs already consumes around 90% of DRAM die area for the current HBM2 configuration. On the other hand, increasing data rate will have significant integrity issues and increase power consumption as well. To summarize, we show the importance of image processing workloads and demonstrate their memory bandwidth bottleneck from both software and hardware perspective. These motivate us to design an image processing accelerator to provide more memory bandwidth. As an alternative solution to compute-centric accelerator like GPU, 3D stacking processing memory architecture provides a promising solution to the memory bandwidth bottleneck. The key idea is to integrate computation logic closer to physical memory in order to increase memory bandwidth and reduce data movement energy. For example, in the current GPU plus 3D memory configuration, data needs to travel a long distance before reaching the destination core. This is bound by off-chip IOs. Some previous work has proposed to eliminate this bound by moving computing cores on the base logic die of the 3D stack, which we called process on base die solution. However, process on base die solution still suffers from limited number of TSVs. Some recent work has proposed to further move the computation logic deep inside the memory hierarchy. The near bank architecture integrates simple logic besides each bank. The bank level bandwidth is around 10 times larger than the process on base die solution. Although promising, the near bank architecture has significant design challenges. On the one hand, the diverse applications in image processing require complex computation and memory access patterns. On the other hand, near bank architecture has stringent resource constraints. On the right, we will summarize the requirements from software and hardware to meet these challenges. First, we need to design a lightweight architecture considering limited resource in near bank architecture. Second, we need a concise yet powerful ISA to satisfy the various computation and memory access patterns in image processing. Third, we need end-to-end software solution, including a well-defined programming interface and compiler optimization specific for near bank architecture. Next, we summarize the 3 key contributions of this project to solve these challenges. First, we propose iPIM, a decoupled control execution scheme for lightweight architecture support. The control core is placed on the base of the 3D stack, while light components are attached to each memory bank in DRAM dice. Next, for flexible ISA support, we design single instruction, multiple bank ISA. The SymB ISA supports SymD computation, flexible data movements, control flow instructions, and synchronization primitives. Last but not least, we propose an end-to-end computation flow called Halide iPIM. The front end is extended from Halide to support new schedules for iPIM. The back end contains 3 customized compiler optimizations for iPIM. In the next few slides, I will introduce iPIM's architecture innovations. This slide shows the high-level architecture design of iPIM. It adopts a hierarchical design with good scalability. On the left, iPIM consists of many cubes linked by interconnect network. Each cube is a 3D stack and is partitioned into many vaults. The middle shows the architecture of a vault, which is partitioned into many PIM dies and a logic die interconnected by TSVs. The logic die contains the iPIM controlling part, and the PIM dies contains process groups, or PGs. The right shows the inside of a PG, which contains multiple process engines, or PEs, and a PG scratchpad memory. The next slide will show more details on the vault design. The key idea of vault architecture is decoupled control execution scheme, where the front-end complex control components of the core are placed on the base logic die, and the back-end simple and memory-intensive execution components are placed on the DRAM dice. iPIM adopts a simple in-order core design, where each cycle and instruction is fetched based on control flow information. In the next stage, the instruction ECU logic will check data dependency for the current instruction. If there is no dependency, the instruction is issued and updated in the issued instruction queue. Depending on the instruction type, the instruction will access vault, scratchpad memory, access remote memory, or broadcast to PGs for near-bank computation. In the near-bank execution stage, simple computations and memory accesses happen in parallel to benefit the high bank level bandwidth. The instructions will be committed and cleared from the issued instruction queue once they are finished. In the next few slides, I will introduce SymB ISA's main features. First, it enables massive bank-level concurrent executions to exploit data parallelism. For example, here we would like to load data from the DRAM banks to the local data register file. A load RF instruction will be broadcast to all PEs through TSVs, and in a uniform PE access, all banks will be activated. On the right, we show the internal structure of a process engine or PE. A PE contains a DRAM bank and some peripheral buffers and logic components. Inside each PE, we adopt SIMD interface between the DRAM bank and data register file to exploit the wide I/O interface, which is 128 bits. To allow divergent access behaviors among each PE, we adopt predicate execution mechanism and add a field called SIMD mask. Here, we assume each instruction can control at most 32 banks, so the SIMD mask is a 32-bit vector. The example shows how to access only the first or the last PE within each PG by configuring different SIMD mask values. Also, as mentioned in the motivations, we support indirect addressing in image processing domain. For example, when we want to access a pixel with given coordinates, we first calculate the DRAM address using address register file. Then, we use the address register file data as an indirect address into the local DRAM bank. SIMD ISA also supports other important operations to enable a wide variety of computation and memory access patterns. Please refer to the original paper for more details. After introducing the hardware design, next, we introduce the end-to-end software compilation support, Halide iPIM. Halide is a widely adopted domain-specific programming language and toolchain for image processing. It decouples the algorithm descriptions and the schedules to hardware mapping, as shown in the below image blur example. We propose Halide iPIM, which extends Halide front-end to support customized schedules for iPIM. We also leverage existing Halide schedules for pipeline fusion and vectorization on iPIM. In addition, we developed 3 backend optimizations for iPIM. For the front end of Halide iPIM, we support 2 new hardware schedules. The first schedule is called iPIM tile, which distribute data into different memory locations in the iPIM hardware hierarchy, as shown in the figure. The second schedule is called load PGSM, which utilizes the scratchpad of a process group, as shown in the figure. This schedule specifies that before computation starts, every PE inside the same PG should load data from the local DRAM banks to the shared PG scratchpad memory. We also preload working set for next computation stage to hide memory access latency. We also leverage existing schedules for iPIM. The compute root schedules specify pipeline fusion. During code generation, this implies a kernel function reading input data from DRAM banks and writing output data to DRAM banks. The vectorized schedule aligns data to improve utilization of the SIMD units. The Halide iPIM backend optimizations have 2 objectives: maximize instruction level parallelism and increase DRAM row buffer locality. Since iPIM adopts a simple in-order core without renaming mechanisms, we introduce register max spanning allocations and instruction reorder algorithms to maximize instruction level parallelism. Also, iPIM relies on high memory bandwidth, so we propose memory order enforcement to improve DRAM row buffer locality. Here, we use a simple instruction trace from image brightening as an example. The pixels will be loaded from DRAM banks using load register file into register file. Then each pixel value is incremented using compute instruction. In the end, the pixel value is stored back to DRAM using store register file instruction. First, we show that the traditional register allocation algorithm to minimize physical register usage will result in register dependency between different pixel operations. In comparison, the register max spanning allocation will try to allocate as much different physical registers as possible. This technique will eliminate the original register dependencies. Next, we show that the computation instructions will stall due to dependency on the previous load instruction. The instruction reordering technique will reorder the instructions to maximally overlap long latency instructions to increase instruction parallelism. In the end, we show that instruction reordering may disrupt row buffer locality. For example, the store of a previous finished pixel may be scheduled before a load instruction of a later pixel. This will reduce the row buffer locality and reduce effective DRAM bandwidth. To deal with this, we enforce memory order so that all loads to the same row buffer and all stores to the same row buffer are scheduled together. In the end, we show the evaluation results of area, performance, and energy efficiency of iPIM. We also show the effectiveness of compiler optimizations of halide iPIM. For detailed evaluation configurations, please refer to the original paper. We first show the area analysis. On the left, we show the decomposition of PIM die area, where the gray part is the original DRAM die area, and the red part is the added iPIM overhead. Here, we conservatively assume 2x area overhead in DRAM process. On the right, we show the area breakdown of the iPIM overhead, where PGSM consumes the most area due to data sharing requirements between PEs. Also, the area of control logic is small enough to fit in the extra area per volt on the base logic die. Next, we show the end-to-end performance and energy efficiency results of iPIM compared with GPU. The green bar shows the speed up and the right cross shows the energy saving. iPIM achieves around 11 times average speed up and 80% energy saving over the GPU baseline. From performance perspective, iPIM benefits memory bound operations like image brightening. For GPU baseline, the histogram benchmark involves data-dependent computation, resulting in inferior performance using halide's default schedule on GPU. For iPIM, it achieves significant performance improvement because the schedule on iPIM converts it into a reduction of parallel reduced partial histogram results. The energy saving mainly comes from the reduction of expensive data movement compared with GPU, since iPIM's compute logic can use the local bank without off-chip data access. Next, we show the results of iPIM compared with process-on-base die solution. For process-on-base die solution, all near-bank components are moved to the base logic die, and these components access their DRAM banks through TSVs. The inferior performance of the process-on-base die solution is because all memory accesses need to serialize on TSVs with limited bandwidth, which is only 10% of iPIM's peak memory bandwidth. The energy overhead of the process-on-base die solution is induced by expensive in-cube data movement energy, which is 2.5 times of iPIM's local bank access energy. In the end, we show the effectiveness of different iPIM compiler optimizations. Here, the OPT represents configuration using all three optimization techniques. The baseline 1 is a naive baseline without any optimizations. And the three other baselines, 2, 3, and 4, is removed of register allocation, instruction reordering, and the memory order enforcement optimizations, respectively. We show that all three compiler optimizations together provide around 3 times speed up. Among these optimizations, instruction reordering is the most effective one, since it maximizes instruction parallelism. As a summary, in this paper, we present iPIM design with 3 key contributions. First, we propose a decoupled control execution architecture. Then, we introduce single instruction multiple bank ISA. We also show the end-to-end compilation flow, which is halide iPIM. Evaluation results show that iPIM achieves good speed up and energy savings compared with GPU and process-on-base die solution with small error overhead. And the compiler optimizations provide significant performance improvement. This is the end of the talk. You're welcome to ask any questions. Thank you for listening.